Jai Hind to all. Today I am here to present the third video lecture of the subject Control System BEC 602, and I am Dr. Amit Garg, Associate Professor in EC Department of AKGEC. So the topic of this lecture is Bode Plot. So we will see how we can draw the Bode Plot for finding the stability of any closed loop system, and also the relative stability corresponding to that system. Means the factors which are responsible for relative stability, like how we can calculate gain margin, phase margin, gain crossover frequency and phase crossover frequency directly through the plot. Okay, so let us start. So the Bode plot gives a graphical procedure for determining the stability of a closed system based on sinusoidal frequency response. Okay, so here what we will do for sinusoidal frequency response analysis, what we will do, we will just put S equals to j omega in the given transfer function. Okay, then the variation of the magnitude of sinusoidal transfer function is expressed in decibel and the corresponding phase angle in degrees being plotted with respect to frequency on a logarithmic scale in rectangular axis. Actually, what happened, this Bode plot is nothing but a frequency response plot. But what is the difference in Bode plot? In case of Bode plot, the magnitude, basically magnitude plot is plotted in terms of TB, and the frequency which we are taking here is on log axis. So by taking the log values, we can accommodate a large range of frequencies also. Okay, so and the plot thus obtained, which is a combination of two plots, that is magnitude plot and phase plot, is known as Bode plot. So what we will do, basically we will take the frequency, log values of frequencies, and along with the log values of frequency, we will plot the magnitude plot. So if GSHS is the open loop transfer function, so we will put j omega in, put S equals to j omega here. So we will get j omega h j omega. So here in this particular case, what we will do, we will take the, for magnitude, we will take the 20 log of mod of j omega h j omega values, and we will plot it with respect to log values of omega, log on the base 10. So this is nothing but our magnitude. This is our magnitude plot. Okay, and for phase plate plot, we will plot angle of j omega h j omega versus log 10 omega, and this plot is called phase plot. Okay, so when we will combine these two plots, we are having a frequency response plot which is called as Bode plot. Okay, so the logarithmic Bode plot has an advantage of being approximated by asymptotic straight lines. So this is the advantage of Bode plot, because we are taking the log values, so you can approximate it using the asymptotic straight lines. Relative stability of a closed loop control system can be conveniently accessed by plotting its open loop transfer function by Bode plot method. So by plotting this, we can easily find out the stability of the closed loop system. The main advantage of this Bode plot is that gain margin and phase margin is determined directly from the Bode plot. Means we can simply measure the gain margin and phase margin by the plot directly, because this plot is this plot is a correct plot. This is not like we have drawn in a rough sense. It is very accurate. It should be very accurate. Only then we can find out the gain margin and phase margin correctly with the help of the plot. So for complicated system, Bode plot can also be plotted from experimental results, and therefrom the transfer function of the system under test can be determined. So this is another benefit with the Bode plot. So this is the advantages. Expansion of frequency range of a system is simple, as we are taking log values of omega. So we can expand it at up to a large extent. Uses of asymptotic straight lines for approximating the frequency response of the system. This is another advantage. Bode plot can be plotted for complicated systems. So for any complicated system, we can easily basically plot the Bode plot, which was difficult in case of, if we will solve that particular, we will find the stability of that system using Nyquist criteria or any other criteria. So relative stability of closed loop system can be analyzed by plotting the frequency response of the loop transfer function of the system using Bode plot. So this we have already discussed. Once we have the Bode plot, then we can directly find out the gain margin and phase margin, and based on the values of gain margin and phase margin, we can easily find out the stability of the system. For the stability of the system, gain margin and phase margin both must be positive. And in terms of gain crossover frequency and phase crossover frequency, the value of phase crossover frequency must be greater than gain crossover frequency. Okay. Frequency domain specifications such as gain crossover frequency, phase crossover frequency, gain margin and phase margin can easily be determined with the help of the Bode plot. Now, there are some disadvantages too. Using Bode plot, it is possible only to determine the absolute and relative stability of the minimum phase system. Okay, so minimum phase systems are those systems in which all the poles and zeros are lying towards the left half of the S-plane. So this is the disadvantage. We can only apply it for minimum phase systems. For non-minimum phase systems, wherein one pole or zero lying in right half of the S-plane, we cannot draw the Bode plot. And corrections are to be made in the obtained plot to meet the desired frequency plot. Means the plot that we have obtained using Bode method is basically the asymptotic Bode plot. But we know there are some errors lying at corner frequencies, which is, you can say, in case of single pole or zero, it is plus minus 3, and in case of double pole or zero, it is plus minus 6 dB correction. So we can easily make these corrections to make asymptotic Bode plot convert into exact Bode plot. So by this particular question, we can see that how we will draw the Bode plot, and how we will calculate the gain margin, phase margin, gain crossover frequency, phase crossover frequency, and also we can comment on the stability of the system. So we can see here, this is the transfer function given to us. So here we can see there is a pole at S equals to 0. So you can say, what type of system is this? This is basically type 1 system. So this is a type 1 system. Okay. So how we will solve it? So first of all, we will put the value of, we will put this equation into standard equation. So we have to convert it into standard equation. So that will become, you can say, that is k upon j omega into k. Standard equation is GSHS equals to k upon s times 1 plus j omega t 1 plus j omega 2t, like this. This is basically, if there is any pole, then you can say it is 1 plus j omega at, like this. And this is n, where n represents the number of poles at origin. Number of poles at origin. Okay, so if one pole is at origin, then it is a type 1 system. So this is our case. Okay, so first of all, we will convert our given transfer function into standard form. So for doing this, we are basically solving it, and then we will put the s equals to j omega. So this is the transfer function, which when we have converted it, we will take 20 and 2 outside from here. So this value will become 2, and all other values will become s times 1 plus s by 2 into 1 plus s by 20. Now for sinusoidal frequency analysis, as we have to draw the Bode plot, so what we will do, we will put s equals to j omega in the given equation. Okay, so it will become g j omega h j omega, and that will become 2 upon j omega times 1 plus j omega by 2 into 1 plus j omega by 20. Okay, so j omega into 1 plus j omega t into 1 plus j omega t1. So when we will compare it, we are having the corner frequencies. So corner frequencies are at j omega t1. So omega 1 is equal to 1 upon t1, and omega 2 equals to 1 upon t2. Okay, so omega c1 equals to 2 radian per second, and omega c2 equals to 20 radian per second. Okay, so these are two corner frequencies. So corner frequencies in case of Bode plot are the frequencies at which slope of Bode plot will become changed. And you can see this is a type 1 system. So starting slope of type 1 system is minus, for type 1 starting slope is minus 20 dB per decade. Okay, so what happened after, so initial slope will be minus 20 dB per decade. Now we will select the starting point. Okay, so this you can see this term 2 upon j omega will decide the initial slope of the Bode plot, and as it is a type 1 system, so initial slope will be minus 20 dB per decade, you can see here. And another term is 1 plus j omega by 2. Here the corner frequency is 2 and 20 radian per second. Okay, 2 and 20 radian per second. And you can see these these corner frequencies are occurring at 2 radian per second and 20 radian per second. Okay, and both these frequencies are corresponding to poles. So what happened, these poles will further introduce minus 20 dB per decade, because these two are simple poles. So simple poles will introduce minus 20 dB per decade. So the initial slope was minus 20. After carrier frequency 2, it will further minus 20. So we are having minus 40 total, and then omega C2 equals to 20. So again at 20, minus 20 dB per decade will be added. So it will become minus 60 dB per decade. So the slope after 20 radian per second will become minus 60 dB per decade. Okay. So now we will draw it. You can see this is basically the Bode plot, and this plot is drawn on the semi-log paper. So first we have to choose the point. From which we will start this Bode plot. Okay. So starting frequency that we have chosen is you can say 0.1 radian per second. At 0.1 radian per second, if you will solve, then at 0.1 radian per second, the starting point will become calculated. How it will become calculated? It will become calculated from 20 log 2 minus 20 log j omega, and this will give you the starting point. And you can see this Bode plot. This is basically the magnitude plot, and this is the phase plot. Okay. So initial slope is minus 20 dB per decade, and the first corner frequency is at 2 radian per second. Okay. So what happened? The magnitude at this frequency starting point is this. This will be calculated by taking 20 log k minus starting frequency is taken as 1. So 20 log 2 from here minus 20 log omega 1. And if your starting frequency is basically minus, if starting frequency is 1, then it will become the value. So you can start from here, and initial slope is minus 20 dB per decade. What happened at frequency 2? Another pole occurs, so now slope will become minus 40 dB per decade, and at corner frequency 20, you can see this another slope of minus 20 dB per decade will be added, so it will become minus 60 dB per decade. Okay. For phase plot, we will simply write the phase equation. Okay. So you can see the phase is of this transfer function will become, this is for real part, it will become 0. A single pole will subtend 90-degree angle in the denominator, so it will become minus 90 in the numerator. So this is minus 90 minus tan inverse omega by 2 minus tan inverse omega by 20. Okay. So this is the basically the phase equation. Now we will change the frequency and calculate the phase at a particular frequency. Here you can see the frequency values are given. Here the angle contribution by each of the term is mentioned over here, and total phase angle is also written over here. So you can see the phase is varying from -96 to -270 when you are varying the frequency from 0.2 to infinity. Okay, so this is basically the phase plot. Now important thing is that when this point where the magnitude plot cuts the 0 dB line is called as gain crossover frequency. Gain crossover frequency, omega GC, and the point where you can see this is the -180 line where phase plot cuts -180 line is basically phase crossover frequency. Phase crossover frequency, it is phase crossover frequency. Okay, it is denoted by omega PC basically. Okay, then we have to calculate another parameters like phase margin, gain margin. So for calculation of gain margin, phase crossover frequency is required. So what we will do, we will take a line and we will draw this line in such a manner so that it will cut the magnitude plot at a point like this point. At this point it will cut. Okay, so the margin from 0 dB till this line is basically the gain margin, and you can see this gain margin is measured below the 0 dB line. Okay, when it is measured below the 0 dB line, then it will become positive. And similarly, phase margin can be calculated if we will draw a line from gain crossover frequency to the phase plot like this, and from -180 degree phase angle. So this is the line of -180 degree phase angle. So you can see here, this is basically the phase margin. Okay, and you can see this phase margin is measured above -180 degree line. So this will become positive. Gain margin positive, phase margin positive. So system is stable. Now you can directly calculate the values of gain margin and phase margin by seeing this Bode plot. Okay, like how this is the point where 0 dB line is cut by the magnitude plot. So it is 2 radian per second. You can see this value is 2. Phase crossover frequency, the line where phase plot cut -180 line, this is. So this point you can see is lying somewhere between 6 and 7. So when you will exactly plot it on a semi-log paper, so you are having this 6.25 radian per second precisely. Okay, so it is important to note that we are drawing it on a semi-log paper. Okay, so in case of semi-log paper, as the frequency increases, the separation between points will become reduced, and this is our linear scale. This is our linear scale. Okay, so depending upon the semi-log paper we are having, in this particular this portion is called 1 decade, 2 decade, 3 decade, 4 decade, 5 decade. So decade is basically the span in which the frequency will become 10 times of the previous frequency. Okay, so it is depending upon how much frequencies we have to accommodate. Depending upon, we will choose the semi-log paper and the scale. Like a small block should be of 2 dB or 4 dB or 5 dB, like that. Okay, so this is how we have calculated gain crossover, phase crossover frequency, and gain margin. So gain margin, you can simply see this is the gain margin. So this is 0 dB and this is basically the 20 dB. Okay, so the gain margin will become 20 dB, and phase margin, you can simply see this is -180 and this is -140. So again phase margin will become 40 degree. So you can see from here that gain crossover, the phase crossover frequency value is greater than gain crossover frequency. It means omega PC is greater than omega GC, and also gain margin, phase margin, both are positive. If both are positive and phase crossover frequency is greater than gain crossover frequency, then the system is stable system. Okay. So in case of magnitude plot, why we have chosen this particular method? Because while drawing the lines based on slopes, there is no requirement to find the value of magnitude at each and every frequency value. Okay. So this is basically the asymptotic straight lines which will describe the magnitude plot. And in case of phase plot, what we will do? We will take some frequencies and get the corresponding phase angles and then join the all the phase values by smooth line. Okay, so that we can approximately get the correct result. Okay, so this is how we will draw the Bode plot and find the stability of the system. Okay, so this is how another problems you can see, and this is the reference that I have taken. Thank you so much.